Right, thank you. Perfect, so when it's my turn to talk, everybody fled the room. Good for me, So, we're about 5 minutes early, right? Lene, are we running a bit? Do you want me to wait for a few minutes, or? Okay, I'll not get into the presentation, or do you want me to? Or?
Yeah, you can dance. No, I'm joking. Yeah, I mean, you can wait a couple minutes.
Yeah, sure. Yeah, I'll talk a little bit about my organization, and I think Anshul, you went through all the major entities in the power sector. You forgot OEMs, original equipment manufacturers. So that's us, Mitsubishi Power, global conglomerate. No need to mention that. I am within the power generation vertical. So Mitsubishi Power is a global entity. So manufacturing your gas turbines, steam turbines, so all power generation conversion equipment. Within that, I am in the Americas structure. So the entity is Mitsubishi Power Americas, which oversees North America, including Canada, and Latin America, Caribbean, Central America. We are based in Orlando, actually a suburb of Orlando, Lake Mary. That's our corporate headquarters. Our manufacturing plant is in Savannah, Georgia, Deepwater Port. That's where all the gas turbines are manufactured, put on vessels, and can be shipped anywhere, North America, South America. Manufacturing also happens in Takasago in Japan. And we have a servicing facility in Orlando. So when it's time to service some of the combustion equipment, that work happens over here. All right, let's see. Yes, we got 2 more minutes. Let me see what else I can tell you about Mitsubishi Power. So with Mitsubishi Power, there is another parent organization called MHI, Mitsubishi Heavy Industries. And within that, Mitsubishi Heavy Industries America, they're based in Houston. So they would do things like carbon capture, industrial compressors, oil and gas equipment. So it's a whole plethora of mechanical technologies. So we work hand in hand with them, with MHI and us, MPWA. We're about 2,000 employees just at MPWA Americas. A lot of them are field service engineers, manufacturing engineers. I personally am in the marketing vertical, although I am a modeler. So my primary background is modeling and market research. And as Mark was mentioning, I have a PhD in mechanical engineering, was doing power systems modeling. So that's where, because the original motivation behind modeling and using Plexos is more on the market side. How do contemporary US power markets operate? So that's why I come under the marketing umbrella in the organization. And there's organization is huge. I think there may be some of my ex-colleagues. I always keep bumping into some of my ex-colleagues. I have one from Wood Mackenzie right there. So it's always great to be here at Xcelerate. And okay, well, let's get going. Well, there are seats up front. It's closer proximity if you want to throw your popcorn and soda cans at me if you don't like what I'm talking about. So I think I have 25 minutes. I'll run through the slides 15 minutes, and we can do 10-minute Q&A. I have about 40 slides. I don't think I'm going to go through everything. This is a pretty in-depth study. And again, the motivation in this setting, I want to talk about the modeling, the Plexos, the software aspects of the study, as opposed to the engineering aspects of what impacts it might have in the real world. Okay, so I guess so. ERCOT decarbonization pathway. What are the modeling solutions? So before you actually go and build real plans, you would run a prototype, just like before building a Boeing plane, you would build a prototype. So you need a model to forecast, like what's the optimum solution in 2050. Okay. This is, basically just that boilerplate, which even Anshul had showed, like, if anything good comes out of this, the credit goes to me. Anything bad happens, it's on you, okay? All right. So fundamental problem in ERCOT, and one of the reasons why we chose to analyze ERCOT, so ERCOT is an islanded system. All the resources are inside, all the demand is inside. So pretty easy to analyze actually from a modeling perspective. So what is the problem statement? And before embarking on any modeling exercise is first state your problem. What's the problem statement? So the problem statement right above, what is the cheapest way to achieve 100% decarbonization by 2050? What is the given condition in ERCOT, okay? You have 4 regions, west, north, south, and Houston. The renewable resources are in the west and south, but your load pockets are in north and Houston. And also today the peak load, system peak load is around 80 gigawatts, and that's going to increase to 105 gigawatts by 2050. So that's a given condition. Problem statement is, so where, when, and how much renewable should you build? So we're talking about decarbonization, how to achieve zero emissions. So how much do you build, where do you build? How do you store that energy? So now because we're talking about, in this particular case, we're talking about intermittent renewables, so obviously comes with storage. How much, when, where, how you should build that. How do you move that energy? Do you move it via power transmission lines? And these distances we are talking, it's upwards of 400 miles from source to sink. So these are typically you're going to do with HVDC lines. So how do you move it? Either you do HVDC lines or do you do hydrogen pipelines? And the economics over there is hydrogen, you're going to make hydrogen, you're going to lose 70% via electrolysis, you're going to transport it, and then you're going to reconvert it to power and other loss. So again, but that's the beauty of optimization and modeling. You put all the numbers in, hit the run button, and you can see what the answers are. And then finally, how should this system be dispatched? So although we are running from 2023 out to 2050, we are running capacity expansion. We are also doing dispatch, hourly dispatch. And there are ways to run this kind of a model, especially because in this case, we're going to be talking about hydrogen as long duration storage, which falls under seasonal arbitrage. And when it comes to seasonal arbitrage, your typical LT expansion cannot be done with your low duration curve method. You need to have a fitted chronology. And once you go in for fitted chronology, you run into computationally what's called the NP hard problem. The computing time goes exponential depending on the size of the problem. These models for us, the run time is around 3 weeks to 4 weeks. Okay. And one more thing I will add over here, the modules and plexos that we have used, because we are dealing with electrolysis-based hydrogen, and hydrogen is a gas, so we are obviously using the power module, we are using the gas module, and we are also using the water module. And the next one, actually, maybe next year when I come and present, I would have included the universal module because we are doing carbon capture modeling now, and that's going to be in the universal module, universal class. Okay, so the quick executive summary, 4 slides. This is what you're dealing with, your power system. And this, what encompasses over here is all known and available power generation conversion technologies. And I'm not going to go through everything of this because typically this presentation takes me an hour or so. What the point I want to make over here, and you can see you have the power side, you got the gas side, you got water, so that's why all 3 Plexos modules. Carbon capture, you have it over there. We'll model a pathway with universal module. Point I want to make about Plexos is you can use the available objects in the power module, gas module, water module. You can, mostly the power module, you can use the objects if it's available directly, like for example, generating unit. But if it's not, you can do an implicit modeling. So you can either model it explicitly or you can model it implicitly. Because at the end of the day, what's behind these objects is energy and mass balance equations. So there are ways you can juggle things around. If you don't have the right object, if you don't have a carbon capture object, well, I can actually mimic that using 2 or 3 other linear combinations of other objects. It's possible to do that. But across the 3 modules, as a modeler, it gave me tremendous amount of flexibility to model actually some of the real world components, either implicitly or explicitly. Okay. So the pathways, so what we call, when we call decarbonization pathways, so we are going from today, 2023, all the way to 2050. So today the ERCOT system is around 124 million tons of carbon dioxide emission. Just for reference sake, the entire United States is 5,000 million tons. So you have to take that system, and by 2050 you want to be a zero carbon system. So you can model different pathways. So pathway one, which is actually happening as we speak, like in the past 5 years and this decade, is you keep adding more and more renewables, you firm it up with lithium-ion batteries. So that's your pathway one, that's our baseline pathway. Now on to that, we add hydrogen storage. And why hydrogen storage? Because us as Mitsubishi Power Americas, we are heavily focused on using gas turbines, hydrogen-capable gas turbines, pair that with electrolysis, pair the electrolysis with curtailed renewables, and you have a storage solution, which actually is an apples-to-apples comparison with batteries. And again, hydrogen as storage does what is called seasonal arbitrage, whereas battery is suited for doing daily arbitrage. So when we model, we see what the benefits are of incorporating some amount of seasonal arbitrage in your portfolio. Okay, so that's our pathway two. Now pathway three, and again, I haven't modeled it yet. We'll do that sometime this year. You can add nuclear SMR, then you can add pre-combustion capture, post-combustion capture, and n number of combinations. And the theory of least cost optimization is you put all these options in, you run linear optimization, and you find out, okay, what's my least cost portfolio solution? And that's what we should go out and build. So today we'll talk about path one and path two, okay? Okay, so given this emission trajectory, this glide path, so 124 million tons today going down to zero, and because the emission of both pathways is the same, so that's the constraint in Plexos we put in. The constraint is the emission constraint. Given the same emission pathway, what we see is pathway one results in a terminal power price, and this is the energy, the generation price, and also the long distance transmission component in it. It's $53 a megawatt hour. So the system is fully decarbonized. The only primary energy resource you have is wind and solar. The only firming technology you have is lithium-ion batteries, and we have three classes, 1R, 4R, and 10R. Resulting power price is $53 a megawatt hour. If you include hydrogen in that mix, that daily, the seasonal arbitrage ability actually reduces your power price by $11 a megawatt hour. And that's the value proposition of doing hydrogen, long duration hydrogen. Okay. All right. And why? Why? So that power price, I mean, these two slides are the same. Like the power price is a function of what the total system cost is. Now, Plexos, when you're doing minimization, you're minimizing sum of total system cost, CapEx plus OpEx, plus VOM, plus FOM, and your fuel cost. So you can look at the system today in pathway one. As you start decarbonizing, you're going to obviously keep incurring more and more new build, new CapEx costs. So over that whole horizon of 28 years, your total system cost is $914 billion, almost $1 trillion. Compared to pathway two, that seasonal energy arbitrage dynamics helps you avoid some of the renewable overbuild. And a very simple explanation, when you think about a 8760 time period of a year, you have your peak load, let's say it's happening in July 15, 6 p.m. is your peak load. And if your system is doing only daily arbitrage with batteries, so you're only moving energy within a 24-hour cycle, that means that primary energy has to be harnessed in the same day. Therefore, your renewables has to be overbuilt in order to capture that much energy to meet that peak load. Whereas when you do seasonal arbitrage, you don't need to size your system for that peak load day. You have a lot of curtailments, otherwise unused energy in the shoulder months, and you can shift that over the months period, and that helps you avoid the renewable overbuild. So that's where the saving comes. You can look at the build cost, the savings between the two. So altogether here you are at $782 billion. So you're reducing this in pathway 2 just by including hydrogen, and this is the net saving. So the cost of the hydrogen capable gas turbine, everything is included over here. So net basis, you're 14% lower. One other significant aspect I want to show you between the systems today and the decarbonized system in the future. If you look today, almost 40% to 45% of your system cost is your fuel cost, because that's the biggest component. As you decarbonize, you look at 2050, there is no fuel. In the future, and we're not going to talk about nuclear over here right now, if your primary energy resource is only wind and solar have no fuel, no VOM. It's only build cost and FOM. That's what your cost components are of your system. Okay. I've got 5 more minutes. This is going to be a deep dive, the next few results. So you got the executive summary. And again, these are all Plex source results, the next 20 slides. So again, how, as that carbon emission constraint keeps getting tighter and tighter, you have to keep building more and more solar and wind. And you can see in pathway 1 for Texas, altogether, your solar plus wind plus battery, you're at 489 gigawatts. And what is the peak load? 105 gigawatts. So that, by the way, is also a very general number in the North American space. The question, if you need, how much solar and wind do I need to decarbonize the system? Tell me your peak load times 4 to 5 times is roughly the number is what you can expect to see. But with the hydrogen pathway, you can see I've added hydrogen-capable combined cycles and simple cycles. And on a net basis, I'm still lower. I'm at 353 gigawatt to serve that same peak load of 105 gigawatt. Okay. So there's about 1 more minute, and I want to open it up for question and answer. We can keep it a little conversational. I'll run through everything. So these are all results coming out of the model. Tell me if anyone want to see any particular one, we can talk about it. I want to talk one particular, the hydrogen system, and what is one of the key takeaway slides from the modeling perspective. So when I said earlier, in this model, and we call this model, I forget to give it a name, internally we call it IDM, Integrated Decarbonization Model. You can actually do cross-sectoral decarbonization with this. So think about applications like ammonia, fertilizers, and so on. Here, power generation, hydrogen as storage. As I mentioned, how it works is, this is the year 2050. In your shoulder season, February to July, when you have that abundance of renewables, which would otherwise be curtailed, that's when you run your electrolyzers. You see the capacity factor of the electrolyzers, so reaching up to 75%. And then when your peak load months, July to September, that's when you utilize the hydrogen and you run your gas turbines and you make power serve the load. And then ERCOT has a small shoulder season in November. So you again make hydrogen, utilize it. Down below here, you can see the water constraint. Now, water is a big issue. Although water is basically, you're consuming water, but when you combust hydrogen, you get moisture in the tail end. So the water is conserved. But water is seasonal, especially when you go to a place like Texas. And here we are modeling Texas West, so Permian Basin and Texas South, Gulf Coast. So they have availability of water. So if you take the month of March, for example, so the dark green over here is showing how much of that water plant's installed capacity is available for generation, so 100%. But how much is being utilized? So there's the availability factor, and then there's the capacity factor. So this is, again, in the water module, we give it a constraint that your availability of your water plant's capacity varies by month. And based on that availability, how much of that is utilized is indicated by the capacity factor. So that's where everything is integrated, and the complexity of that future decarbonized system is such that really you cannot isolate these things and solve. You cannot solve power system first, find out an answer, do gas, iterate, go to water, iterate. That really is a very cumbersome way. And the thing is, which I really appreciate about Plexos, is the integration across these modules is such that it helps me capture that real world dynamics without having to iterate. And it's a one-shot solution. Everything comes out and everything is intact. Every molecule is accounted for, whether it be water, it be gas, it be power, an electron. Okay. And I will go to the last slide and then we'll stop over there. Yeah, the conclusion slide, there you go. So finally, between the two pathways, and this is a question to the PUC in Texas and of course ERCOT themselves, what kind of system do you want in your future in 2050? Do you want to be in pathway one where you only do renewables plus lithium ion? So this is your system. You have to build out your transmission from what you were today. So you need about 27 gigawatts going from west to north, 5 gigawatts west to south. Total system price incurred over that whole 28-year horizon is $914 billion, resulting power price $53 megawatt hour. Compared to if you include your hydrogen, so you add some electrolyzers, you add some hydrogen storage, this is salt cavern geological storage, you add water plants, you add some combined cycle and simple cycle hydrogen gas turbines. That way you offset a lot of the renewable overbuild, you offset some of the lithium ion batteries, you move some of your power via hydrogen pipeline. So that's the other aspect we model, hydrogen pipeline using the gas module. So instead of doing HVDC lines, you can move some of it via hydrogen pipelines. And therefore you would end up with a total system cost of $782 billion, a power price of $42 a megawatt hour. This is the question in front of the PUC, which one do you want? Do you want to be in that system or this system? And obviously, consumer price theory is like, you want the lowest cost, lowest power price to the consumer. Okay, so, and the rest is all the accounting table. So this is all the accounting table. And assumptions, we typically use NREL, ATB, SNL, IHS. There are some DOE studies on water availability. All of this is public domain information. Nothing is confidential to Mitsubishi. So you can cite this. These are the sources. And that's it. There's about 6 minutes left. I want to sort of open it up to Q&A, and if we can have the mics around. Yeah.
Mike Horshak from Charles Rivers Associates. I was just wondering, what was your assumed supply level of water? Did the model just assume if you paid the price, the water would be there, or did you put in some volume constraint in this analysis?
It's a physical constraint. It's not elastic to water price. So based on seasonality, you actually have a limited amount of water available. So it's a kilogallons of water each month. So it's and actually in the real world also, you can't, just because I can pay a higher price doesn't mean I can have more water. The water has to exist. So I hope that answers your question.
Yeah, Nathan with E3, just a question. You said 3 to 4 weeks for a solve time. I'm wondering kind of what kind of infrastructure you use for running the model, or if it's on the cloud.
Yeah, we don't use cloud, so we have an internal machine. The issue why it's 3 to 4 weeks is because it has to run sequentially. So you have to solve 2023, 8760 granularity, move on to 2024. And that's why it takes. And you're running, as I mentioned earlier, when you run fitted chronology, you're doing LT and ST in the same problem. So you're getting dispatch and capacity expansion. So it's a complex problem. So by nature, the computing time is higher. And we can't really solve the next year until this year's solution is solved. Yeah.
Next question here is, how did you model hydrogen? Did you model as a field price similar to like a natural gas price, or did you model the fixed cost of the electrolyzers, and how does that factor into like the total system cost?
Yeah, so hydrogen is modeled as storage. So there is no hydrogen price. It's not $1 per kg. Basically, renewables, so the model is building renewables, okay? Then it sees, oh, I have a lot of curtailment. then it has the option to do electrolysis, store it in a salt cavern, move it via pipeline, and then it has the option to build a hydrogen gas turbine. And so when it looks at the economics of those, and then, again, linear programming compared to battery plus renewable, it chooses hydrogen.
But you're also modeling the electrolyzer load, the storage, the additional load as an energy storage resource, right?
Right. So, but the electrolyzer load is decided by the model. The model decides when to run how much electrolyzer to build and when to run it. That is decided by the model, and that is decided based on when the curtailment will be happens. Yeah. So there is no. Let me put this, I'm not fat fingering in anything in this model. The only inputs that goes in are those assumptions which you saw, and which is basically just cost information, cost, CapEx, build cost, FOM, VOM, fuel cost. And there's no fuel, hydrogen is not a fuel over here. Hydrogen is a gas. And you run it, and basically once you start the simulation at 2023, again, there is no interruption, there's no fat fingering. It takes the solution from the previous year, sees, okay, this year I have to reduce my CO2 emission by so much, so I need to build so much more, and then I need to run so much more, go out all the way to 2050.
So you've got a really interesting problem here with, effectively, you've got a system with no fuel cost, just variable O&M at the end of the build out. ERCOT's an energy-only market, hypothetically. At some point in time, does the question of, is that the right market structure really come into question? Because you've really got just a fixed cost recovery situation. And,
right.
Yeah. I guess kind of a little off the topic, but.
No, absolutely. Actually, I was having lunch with one of the ERCOT markets people. It's like, all good, but hey, we are like an energy only and most competitive. We want cheap energy and we don't really care, like in our markets, what the emission are. So this study is not, so let me ask you or like the audience in return, right? So we want to decarbonize, okay? No one's arguing. I mean, ERCOT, okay, let's leave aside. The reason we chose to study ERCOT is, first of all, modeling-wise, it's very easy for me because it's an islanded system. I don't have to run the whole EI or the whole WEC. So that's one, okay? The other is, if you look today, the most critical market where proof of concept has to be established for any technology, one is ERCOT, Texas, other is Germany, and the other one is Japan. No offense to Australia, energy exemplar. So Germany, Japan, and Texas, if you can solve these three markets, show that a certain, and again, from our perspective, we are an OEM, so we have to build those products. So we have to first find out which product is the most reasonable one. So that's why we chose ERCOT. Now your question, what ERCOT does, like if they say, hey, thanks, great simulation and everything, but we don't care about decarbonization, so be it. Then the existing market continues. But if they say that, okay, we do want to decarbonize, eventually we want to be a zero carbon system, then they have to change their market construct. And one, I don't know if Stephen is here, Stephen Broad here, because last Energy Exemplar meeting we were having a conversation. Think about how a dispatch curve happens, a supply curve. So your lowest point, okay, and that supply curve is basically your short-run marginal cost. And what is short-run marginal cost? Fuel cost, heat rate, and your variable O&M. That's how all your ISOs are dispatching. Now, if you go to a decarbonized system, primary energy, just renewables, no fuel, no heat rate, no VOM, what's a short-run marginal cost? Nothing. How does your model dispatch? How does your market operate? It's a totally different world we're going to be in 2050. This current construct is not going to work, where bid the lowest, and you're going to bid your short-run marginal cost, and the profit margin you're going to pick up is the difference between your short-run marginal cost and the highest bidder. That simply is not going to work if you want to decarbonize in the future. So I hope that answers your question, or at least gives some food for thought.
Final questions? All right, thank you so much.
All right.
Fantastic session.